This is part 3 of 5, and in this section we are going to be talking about continuous time Markov chains. So what we saw in the discrete case was, if you define one-step conditional probabilities, you can get to any conditional probability as long as you know the initial condition. And from conditional probabilities, you can get to any joint probability. So the one-step conditional probabilities constitute the parameters of the model. And that's how you fully define a discrete time Markov chain. We're going to see that if we make time continuous while maintaining the state space to be discrete, it is still enough only to show your parameters as a directed graph or as a matrix, but they mean something slightly different. So we're going to get to a fuller explanation, but just as an introduction, let's go back to our classic healthy, sick, dead model. Sigma for sick, rho for recovery, mu for dying, and nu for dying from the sick state. In the continuous time Markov chain, these do not represent probabilities anymore. They represent rates. In other words, they can be greater than 1. If you represent this information as a matrix, this will be sigma, this will be mu, this is recovery, this is nu. 0, 0. So in the discrete case, we would have said once you're in the dead state, you stay in the dead state with probability 1. But we are actually going to require, for reasons that you'll see soon, that the rows actually sum to 0. Because that diagonal actually holds useful information, keeping in mind that these are no longer probabilities. As before, we are going to use the notation, the probability Pij is just a conditional probability, an important probability for us to be able to define the process. The probability of going from state I to state J over the time period T. So let's quickly have a formal definition for this process. A random process is called a Markov jump process or a continuous time Markov chain, where the state space is still discrete, but time is now continuous. This time, we cannot list our time periods as we did in the discrete case. So you'll actually see that in the conditional, we have a set. And this set represents the history of the process up until that point. This is formally known as a filtration. And the notes don't go on to formally define a filtration, which is a little bit of a problem for us to be able to manipulate these equations too much. There'll only be 1 or 2 examples in proofs where we actually manipulate a filtration. But all in all, because this is an applied course, we kind of stop at some of the theory and we focus a little bit more on the application. So this is the formal definition of a continuous time Markov chain. So now, how do we get those conditional probabilities that we need to be able to calculate our joint probabilities? Well, this formula says that we cannot easily necessarily get the conditional probability, but we can get the derivative. And the derivative is an expression of other conditional probabilities and a set of rates. And these set of rates are what we had in that matrix at the very beginning of this section. So it's a set of rates that can be larger than 1, defined in a matrix where the diagonals are minus the sum of everything else so that they sum to 0. And so that generator matrix, along with other conditional probabilities, can give you one conditional probability. And you'll see here that we sum through, I and J remains constant, but K is allowed to vary. So you're basically summing through all possibilities in the state space K. Because this formula is valid for every possible pair of states in our discrete state space, we can actually represent the conditional probabilities themselves as a massive set of matrices, where A is that generator matrix. Let me just make that very clear. So this is known as the generator matrix. Okay. Let's quickly prove it. I'll draw your attention to this very first bit. So this probability this derivative is just what you're used to from high school maths, where the derivative at t with respect to t is just t plus h minus the function at t, all divided by h. So there's a little assumption in there. We're actually assuming that our probabilities form a continuous function, but it's a minor assumption in most cases. Then I want to draw your attention to a few definitions, some more derivatives that we assume exist. We assume that this limit exists, and you'll see in a second why it's reasonable. We also, this is for a case when the pair of states that we are interested in are not the same. But where the states are the same, I, we make the assumption that that limit exists. We also have two boundary conditions. The probability of going from state I to state j at point 0. There's no time in which to switch states, we assume is 0. And the probability of leaving or of staying in state I, given that there's no time to leave, has probability 1. So these are the assumptions that we're making. And then we have 4 steps here of a proof. So first we just, we make use of this, a similar Chapman-Kolmogorov equation in the continuous case. So the probability of going from I to j in the time period t plus h is the same as going from I to k in t, and then from k to j in h, as long as you're summing across all possibilities. So that's the intuitive version of this step. So this is the Chapman-Kolmogorov equation for the continuous case. Then we just go out to separate those pairs where the states are the same and where they're different. So here we have the JJ, and we take that out of the summation. And that's only because these definitions are slightly different at the top. Substitute in these limits that we assumed existed. Substitute the definitions, and we get the formula at the top. Great. So here's just a slightly practical question. Consider a continuous time Markov chain, healthy sick dead model with transition rates rho, sigma, and mu, but this time assume that mu is both equal for healthy and sick lives. For a specific life, define the conditional probabilities as we have, where xt denotes the state of the life concerned at time t. So this is really all very standard notation. Derive from first principles a differential equation satisfied by PhD, and hence show that PhD is fully, so the probability of going from healthy to sick in time t is defined by this function. The key in this question is actually the fact that we need to do it from first principles. So it's the same as first principles from school. This refers to first principles. Here's what we have here in the top right. We care about the probability of going from the derivative of the probability of going from healthy to dead. We literally repeat what we did in the proof on the previous slide, but this time we've got explicit states to work with. So if we're saying sum over the whole state space, we know that we mean healthy, sick, and dead only. So now we have actually come up with differential equation in terms of other conditional probabilities. So normally when a question asks you to calculate conditional probabilities, it will be more than happy if you just jump straight into applying the formula. It's only when it occasionally asks you for first principles where you have to prove it, like that block on the right. So we know that the probability of, so let me just draw some attention to the shape of this, this formula. The probability of going from healthy to dead is the same as the probability of going from healthy to healthy, healthy to dead, healthy to sick, sick to dead, healthy to dead, dead to dead. So you'll notice that on the left-hand side of the equation, you're really fixing these parts of your expression. And then in the middle, we run through the entire state space: healthy, sick, and dead. Okay, this is the Kolmogorov forward differential equations, so the probabilities come at the front, if that helps you to remember it. You'll be doing lots of these examples, so applying this formula will become second nature with only a few examples. So we take out the mu in this next step. We divide by the function on this side. We integrate both sides between 0 and t. So that's what we did in this step. Integrate between 0 and t. And it simplifies to the expression we were looking for. I also want to point out that if a question asks you to show that something is true, as it does in this case, it is actually enough for you to take the answer from the question, plug it into the left-hand side of the expression you're trying to prove, and plug it into the right-hand side and show that they are the same. So often people go through a lot of effort in exams to try to prove that this expression holds when they could have just used the answer from the question to prove that it's the case. It's often easier to do it that way. It's just a side note. On the next slide, we're now going to talk about an alternative. It is theoretically identical to the four differential equations, but this time the backward formulation of it. But you can see that you can calculate exactly the same probabilities as we had in the forward case, but this time putting the probability after the rate. So these are known as the backwards differential equations because the probabilities come at the back. And similarly, you can express all the pairs of all the states as a massive set of matrices. I'll just quickly draw your attention to it. Here's an example of a matrix that contains all your conditional probabilities. This is the probability of going from state I to j, where it's already solved for you. So this PT in this question is an example of the PT we have in this question. Cool. A theorem which we have now proved implicitly. A continuous time Markov chain is defined by S times S, which is the size of the state space, minus S transition probabilities. So it's all the non-diagonal rates of our generator matrix. The values inside a generator matrix are known as transition intensities. So this proof really is very simple. It just says we have shown that the conditional probabilities exist, and from conditional probabilities you can get to joint probabilities. Okay, a somewhat simple question. Consider a simplified model of a credit rating of companies in continuous time described below. There are 3 credit ratings which a company can have, namely A, B, and D for default. And possible transitions are as follows. You go from A to B, B to A, and B to D. The transition matrix is as follows. So what this question has done is they've already solved your differential equations for you to get to the conditional probabilities. Calculate the time after which a company starting with an A rating is more likely to be in state D than in state A. So as with all questions, all Markov chains, it's always useful to go draw a picture because the picture doesn't just informally help you understand what's going on, it also is your formal definition of the model. So you can go from A to B with a rate for alpha. You can go back with rate alpha, and you can go from B to D with rate 3 alpha. And just from looking at the picture, you can now make a little bit of sense of the question. It says, what is the time when it's more likely for you to be in state D than in state A. And the reason this question makes sense is if you start off in A, the people are leaving A at a rate much faster than they are returning, and there's a non-zero chance of you going to the death state. So if you start off in A, at some point it's going to be more likely that you end up in the default state. So the question is actually quite simple. We're looking for the conditional probability of starting off in state A and ending in state A at time t. When is that probability less than the probability of going from A to the default at time t? And as we said, that they've done all the work really for you by solving your differential equations, your Kolmogorov differential equations, and they give you the conditional probability. So this is just a simple matter of solving the inequality. And you'll see that it actually gives you a numerical answer. Okay. One thing I want to point out, if we talk about the probability of going from A to A at time t, that is not the probability of staying in A and then for the, for the first time leaving A at time t. The probability of still being in A at time t very much leaves open the possibility that the individual in question have gone to B and come back multiple times. If you're interested in the probability that someone stayed in state A and have never left, the notation that we use just puts a bar over the A. So we call this the holding probability. And that's an important distinction. It's going to come up all the time. This is our first opportunity to solve some of those differential equations. A continuous time Markov chain is defined by the following transition matrix or generator matrix. Calculate and interpret all conditional probabilities. So just to draw it, I might have done it on the next slide. It starts with an origin state, a 0 state, and it's possible to go to 1, 2, 3, 4, all the way to n, but it's not possible to come back. So that diagram is the equivalent of this matrix. It's worth pausing the video and trying to plug in the values of these rates into our either backward or forward Kolmogorov equations and seeing what you can come up with. So to be able to calculate the transition probabilities, it depends what states you're interested in. If it's between going from 0 to 0, the probabilities will definitely be different compared to going from 0 to any other state. But going from any state other than 0 is not possible. So there are two cases. Either I is equal to j for our conditional probability, or j is not equal to 0. That is the two cases we're interested in. All other cases, so I guess we should say case 3, is otherwise. And in that case, the transition probability is always 0. So I just wanted to set out the cases before we jump into solving them. So the first one is where we're staying in state 0. The reason we say staying is because we can see that once you leave, you don't come back. So going from 0 to 0 is actually the same as continuously staying in state 0. And we apply the forward differential equation. So with a forward differential equation, the probabilities come first, and then the transition rates come second. We have 0 to 0, 0 to 0, and 0 to 1, 1 to 0. That's a little error. Then we have 0 to 2, 2 to 0. And it's very quick to see that coming from anything to 0 will always be 0. So all of the terms except the first one collapses to 0. Here we have minus mu, the diagonal of the transition matrix. We can divide this on the other side. Then we can integrate both sides between 0 and t, and we come up with the exponential distribution. We'll show after this example why that's actually a general finding. The holding time of any state in a continuous time Markov chain is always exponentially distributed. The notes only partially proves it, but I think we'll prove it in its entirety. Moving to case 2, we apply the 4 differential equations again. So you can see that the indices at the beginning and the end will always be 0 and j. And then we cycle through the whole state space in the middle. So 0, 1, all the way to j, then to n. Moving from anything to anything that isn't 0, like as we have in these 2 terms, the second and the fourth term, will clearly be 0. So we don't have to worry about them. The probability of mu going from j to j is a possible exception. But keep in mind on the previous slide, once you're in one of these states, you can't go anywhere. And we said that the rows of a transition diagram for a continuous time Markov chain must sum to 0. So in fact, this term is also 0. It is just the first term that survives. And the probability of moving from 0 to j is just lambda j. And just simplifies because we solved 0, 0 in the previous question. And we can then set out to simply solve and integrate between 0 and t again, and it simplifies to this. So putting it all together, here case 3 is actually in this final answer. So here you can see that we've got the case where we're staying in state 0, we're moving from 0 to somewhere, but nothing else has a non-zero probability. Next, we're going to show that the holding time or the waiting time in a state of a Markov jump process or a continuous time Markov chain is always exponentially distributed, and that the parameter for that distribution is always minus the value on the diagonal. In other words, the waiting time in a state is exponentially distributed, and the parameter is the sum of the values of all the arrows leaving that state. We're going to do that in 2 steps. First, we're going to show that the holding time has the memoryless property. Then we're going to show that there's only one distribution that has the memoryless property, which is the exponential distribution. So let's quickly define the memoryless property. We're saying, what's the probability of waiting longer than s plus t, given that we've already waited s? Now, if that answer is equal to the same as waiting longer than t, then your distribution, not process, your random distribution has a memoryless property. So this is just a random variable again. Don't think about this in terms of a process. And as we said, we'll show that this actually only ever works for the exponential distribution. So let's make this a little bit more concrete. We're calling this a holding time or a waiting time. So think about it as waiting in a hospital or waiting for a bus or taxis to come down the road. If I've waited longer than 10 minutes, what's the probability that I'll wait for longer than 30 minutes? Well, if it has the memoryless property, we're saying it doesn't matter that you have waited. It's the same as just saying you're starting to wait again from scratch. You're waiting 20, it's the same as waiting for 20 minutes. So this holding time, this particular one, which we said the exponential distribution has, is actually not quite correctly thought of as, say, waiting for a bus. If you are waiting for a bus and there's a fixed timetable, if the bus comes once every 10 minutes, then having waited 10 minutes actually already tells us a lot about what's going to happen. A bus is probably just around the corner. So the probability of waiting another 30 minutes is actually close to 0, or very unlikely. This waiting time is a lot more like waiting for a taxi next to the road, where taxis arrive at a fixed rate. So you can, once we've finished this proof and you use this fact all over in solving questions, you can always think about waiting for in a state of a continuous time Markov chain in general as waiting for something like a taxi. It's always like that. Cool, so first we're going to show that this memoryless property holds. So we're just showing that this is equal to this. So let's start just by writing out this probability in a little bit more detail. Remember, we're talking in continuous time. So we're now talking about the holding time. the holding time can also be formulated as saying that our random variable stays in state X for all of time between 0 and t plus s. Given that we stayed in the state X for all of 0 to s, that's just writing it in normal mathematical logical terms, or quantifier terms. We can say, because of the definition of a conditional distribution, you can see that these two bands overlap between 0 and s. So here, this 0 can be replaced by an s. And that's just the definition of a conditional probability. We know that we were still waiting by the time s started. Okay, moving to the next step. Knowing the whole history of the process isn't necessary because we have the Markov property. So the filtration, or in this case, the history of the process, it's more than enough just to know that at point S, we were still in state X. Finally, we can move this whole process along to the left from S to T plus S just to 0 to T, because we know our process is time homogeneous. And this is just the definition of T greater than T. So we have now already shown step 1 that the holding time has the memoryless property. And we just used sort of the quantifier notation of our random variables. Next, we're going to show that there's no other distribution that also has this property. Start by just defining Pt greater than T as GT. Also take the left-hand side of the equation and express it properly as its conditional probability. So I think you will remember the probability of A given B is equal to the probability of A intersection B divided by the probability of B. So that is all that so assuming the memoryless property holds, this part of the left-hand side of the equation simplifies to this, because the overlapping of this event and this event is just equal to T plus S. T plus S is completely contained in T larger than S. That set is contained in T larger than S. So the intersection of them is just the smaller of the sets. So if your random variable has the memoryless property, we know that this holds. And therefore we know that GS plus T is equal to G times S times G of T. And we can iteratively apply this, this property to itself to show that G to the T is equal to G to the 1 times T. We can raise the second side of the equation by e to the ln. And we can express ln G1 as a constant. And therefore, we know that GT has the shape of minus e to the some constant, which we just call lambda t. So if your probability distribution has the shape of e to the minus lambda t, that is the cumulative distribution function of the exponential distribution. Remember, the cumulative distribution function is 1 minus e to the minus lambda t. And we are actually looking at 1 minus the cumulative distribution in this proof. So that's how we know that if the memoryless property is true, that your cumulative distribution function takes the shape of an exponential distribution. So this is proof that we did very clearly and is definitely testable. But normally you wouldn't prove it every time you used it. It's something that we use all the time. It probably comes up in every continuous time Markov chain. So every time you use it for 1 mark, it's worth stating it explicitly. Don't use the theorem without stating it, because you might be giving up a potential mark. Theorem 3.3 is done without proof, but it makes a lot of logical sense. It's a formula for the expected time of moving from state I to state K. So the expected time of moving between any two states in continuous time. And now that we have proven that the waiting time in state I is exponentially distributed, we actually know, like I said, we don't have to prove this, but intuitively, it starts with the expected time staying in that state, and then the expected time it will take to get to the other state you're interested in, which you can see here, it's an iterative definition. The formula itself depends on further expected times. Okay. Despite that, here's the formula. The probability of moving from I to K is a number relating to I. It's the look for state I in your generator matrix and take minus the 1 over the value of all the arrows leaving that state, or the value in the diagonal, plus the same number multiplied by, and this looks a lot like the backward differential equation where we have the transition rate and then some function in the second bit. But this time, we still fix the beginning at the end, I and K, but this time we cycle through the whole state space except the two states that we're busy with. So we cycle through all the states except I and K. One example will really help you to memorize this formula. I'm not sure if this formula shows up in the formula sheet, but it is definitely worth learning. Example 3.4 is here to just solidify what we've learned so far. So it's going to allow us to apply some of the Kolmogorov equations, theorem 3.2 and theorem 3.3, and a little of common sense. So here's another variation of the healthy, sick, dead model where we're now adding a terminating state. And then here are some of the questions that we are trying to answer. Draw the transition diagram. That's standard in any case. Calculate the probability of being healthy for at least 10 uninterrupted years, given that you are healthy now. So that is the holding probability, and we showed in theorem 3.2 that that is exponentially distributed. On the day that a sick life stops being sick, what is the probability that X has recovered? See if you can use common sense to come up with that probability. Write down the expected duration of a terminal illness starting from the moment of the first transition into the state T. Also an application of theorem 3.2. Let dj denote the probability that a life which is currently in state J will never suffer a terminal illness. Calculate the probability of a healthy state never suffering a terminal illness and the probability that a sick life will never suffer a terminal illness. Finally, calculate the expected time before a healthy life becomes terminally ill. That's a flat out application of the formula 3.3, which is just saying what's the expected time for a healthy life to become terminally ill. Okay, it's worth taking out a piece of paper and trying this before you see me work through the answers. Okay, this is the diagram. You can see that once you're in the terminating state, you can't leave. You have to only go to the dead state. Here we know the holding time of a healthy state is exponentially distributed, where that exponential parameter is the sum of all the arrows leaving H. So 0.05 plus 0.05, which is how we got to that 0.1. We care about the probability of being healthy for at least 10 uninterrupted states. The cumulative distribution of the exponential is 1 minus E, as you might remember, to the minus lambda t. But because we care about at least 10 uninterrupted states, it's 1 minus the normal cumulative formula for the exponential distribution. If you work through the details, you'll get a 36% chance. On the day that a life stops being sick, what's the probability that that life recovers? We don't actually prove this statement, but it gets used in questions all the time. It is just the probability of leaving the state to the sick state divided by the sum of all the possible transitions out of the state. So just going back to this, you could ask yourself any question. What is the probability that when a life leaves the healthy state, they will die? It's this probability, 0.05, that transition rate, not probability, divided by the sum of everything outside of that. So the sum of the two, 0.1. And that is true in any case. Obviously, in the terminal illness state, what's the probability that you'll go to the dead state when you leave? It's 0.4 divided by 0.4, which is a certainty. So it works for any state. The next question says, write down the expected duration of a terminal illness. Again, an application of theorem 3.2. It is just a expected value of an exponential distribution, which comes to 2.5 years, or 1 divided by the 0.4 parameter. Number 5 is arguably one of the more tricky questions. Well, what's the probability that a healthy life will never reach the terminal illness state? Well, if it could potentially, when it leaves, if it leaves for the dead state, that's one possibility. Or what's the probability that it leaves for the sick state, but then never goes to the terminal state from the sick state? Well, we have a symbol for that. That is ds. So remember, when we think about alternative events, we sum them in probability theory. So the probability of never going to the terminal illness state from the healthy state, either you die and straight from the healthy state, or you go to the sick state times the probability that you never get to the terminal illness state from the sick state. And the same goes for the sick state. There are two ways in which to never get a terminal illness. You can either die, so that in that case, it would be 0.1 divided by the sum of everything leaving, all the arrows leaving the sick state, which is 1.2. So you can either die straight from the sick state, or you can recover, which is 1 over 1.2, and times the probability of you never getting the terminal illness from the healthy state. So it's that dependence between these two variables that gives us two equations with two unknowns, and you can solve. And now we are just plugging into the formula for the expected time of going between the healthy and the terminal illness state. And that formula might be a little bit daunting at first, but we are going to get to some examples, hopefully, where you see that it has a very intuitive explanation. But for now, I just expect you to sit with the formula for theorem 3.3 in front of you and plugging it in for this particular case. You'll see that when you plug it in, you kind of left with more questions than answers. You'll see that some things go away, like the expected time of going from death to the terminal illness state is 0 or infinity, but anything that's infinity in this formula, just you can use 0. And then you'll just reapply the formula to MST to get, again, two equations with two unknowns. And that's often the case with these expected time questions, because the expected time is always expressed in terms of other expected times. It's the same with the Kolmogorov equations. Your conditional probabilities are stated in terms of other conditional probabilities. So it almost always amounts to you solving a simultaneous equation or a differential equation. Up to now, we've only looked at the probability theory of the problem. In other words, the parameters are already estimated and we're just asked to calculate a whole bunch of probabilities. We're now ready to look at the statistics of the problem. In other words, coming up, estimating these transition rates. So consider again a healthy, sick, dead model. You can see it's a very popular model in this course for a terminal disease. So the transition intensity from healthy to sick is sigma. There's no recovery state. moving from healthy to dead has mu as before, but moving from sick to dead has mu plus some additional force of mortality. So there's no recovery in this question. We're now going to estimate these parameters based on data. The first question asks you, describe the data you think you will request or that you should request for a population of identical healthy lives in order to estimate the parameters of this model, okay, intuitively. Well, firstly, if all the lives are identical, we'll actually need the total time spent in each state for all the individuals. And we'll also need the number of transitions between all pairs of states for all individuals. If we are still deciding what our homogeneous groups of people are, we'll have to ask for a unique identifier for each life, as well as some fields that describes information about these lives. If we're still deciding, say, what rating factors to use for an insurance policy, for example. In that case, you'll need not just the information in aggregate. If you're going to work with individual information, you won't need the information for all, but for each individual. But if you've already grouped people in terms of homogeneous lives, then it's more than enough to just know how much in total they spent in the state and how many people moved between the states. So if that wasn't intuitive to you, it will become more intuitive with a few questions. Okay, so here is a summary of the data that's available to us. Let's just draw the matrix or the Markov process diagram again. So we know there's no recovery rate, so that's sigma. There's a mu for dying and a mu plus alpha dying from this terminal illness. We have the amount of time spent waiting in healthy and sick, and we have the total number of transitions between each pair of states where transitions are possible. So that's healthy and sick, healthy and dead, sick and dead. The second question asks us to write down an expression for the likelihood of these three parameters. We're going to prove that this is the expression in detail in exercise 4.2. So just wait for that point to prove it. But for now, you can then just take this for granted. You're going to take every transition, as we have in here, alpha plus mu, mu and sigma, and we're going to raise it to the power of the number of times that we transitioned between those two states. So sigma is to healthy to sick, which is 103. Mu is healthy to dead, which is 50. And you're going to do that for each sigma. Then you're going to multiply that by e to the power of minus, and then each of these e's will represent a state. At the top, you're going to multiply the amount of time you spent in that state by the parameters leaving that state, and you're going to put a negative at the front. Here you can see, because there are no transition rates leaving dead, that row sums to 0, so it doesn't matter how much time we spent in the dead state, that term will just go to 1. Okay, so I explained this likelihood function, not how we got to it, but just what it is. And you're going to see that we're going to prove it in detail a little bit later. Use this likelihood to find the maximum likelihood estimate for these three parameters. As we always do with likelihood functions, we're first going to take the log because it's simpler in almost all cases, because the likelihood function is always the multiplication of marginal distributions, and log always allows us to, with a plus sign, to split out each of those terms. So by taking a log and then differentiating with respect to, so here it's actually the log likelihood with respect to sigma. If you work through the detail, you're actually going to see that sigma hat is equal to 103 over 1,000. So to estimate this rate, it's very intuitive. Again, as before, we take the number of transitions between the states, 103, and because it's coming from the healthy state, we divide by the amount of time spent in the healthy state. And that's actually a general truth for all continuous time Markov chains. So here again, this is the rate at which things happen. And we showed that the maximum likelihood estimate actually neatly coincides with our intuition. And similarly, to drive the point home, for mu, the number of healthy to dead cases was 50. And the amount of time spent in the healthy state, again, is 1,000, the same as we had 1,000 for the sick on that side. For alpha plus mu, there were 32 cases, and this time we're coming from the sick state, and that's why we're dividing by 100 over here. And these are our maximum likelihood estimates. Sorry, that is just a small correction. Describe a way in which the approximate variance of the estimator sigma can be found. Okay, this is another formula that's given to you in the notes. Sigma hat, the estimator, is asymptotically normally distributed where the expected value is the true parameter and the variance is the true parameter divided by the expectation of the time in the state that it's coming from. Okay, so this is a formula you can take. It uses the central limit theorem. The proof is in the notes. It's maybe 3 or 4 pages, and it's worth going through it yourself before seeing someone else do it. I'd also think the explanation in the notes is pretty good. Okay, next slide is about simulation in continuous time. Okay, we already covered simulating in the discrete time. It asks us to describe the steps one will follow to simulate from a time homogeneous continuous time Markov chain. So as before in the time discrete case, we always have to assume that we can't simulate numbers from a distribution. We're always simulating numbers from a uniform distribution. And this is just because this is the way it happens in practice with computers, whether using R or whether using the random variable generator in Excel, it will always produce a number between 0 and 1, uniformly between 0 and 1. And that's because there's such variety in the types of distributions you want to simulate from, and it's normally a very simple inverse one-to-one function calculation to get to simulate from anything else. It's actually easy to think about if you just split the problem up into 2 pieces. So first, let's ignore the amount of time we spend in each state. Let's just simulate the path that the person moving in continuous time will follow, ignoring the amount of time they spend in each state. And we can do that because we know the time a person spends in this state is independent of the history of the process, and it's exponentially distributed. So we know that fact separately. So let's start with step 1, just simulating the path that the person in this process follows, ignoring how long they spend in that time. So just starting again with the standard healthy sick dead model, we can translate these rates, which we said could be greater than 1. We translate these states into things that sum to 1. So sigma divided by all the things leaving the healthy state, mu and sigma, these sum together to 1. Same for the sick state. So now we've turned a continuous time Markov chain into a discrete time Markov chain, but ignoring the amount of time we spend in each state. And to be able to simulate the path, which will look something like, starting healthy, 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 sick, sick, healthy, sick, dead, maybe. That's an example of a simulation. For this first step, you're going to follow exactly the same process as we did in the discrete time case. We've already covered that. You can just go back if you don't remember. Step 2, we will now assign to each of these states in the simulation, we're just going to assign to it the amount of time we waited in it. So it could look something like 15 minutes, 30 minutes, and then simulating from a continuous time is literally writing, we spent 15 minutes in the healthy state, then we spent another 30 minutes in the healthy state, then we spent 2 minutes in the sick state, then we spent another 3 minutes in the sick state. This is what a simulation from a continuous time will look like. So we take a second vector of uniformly distributed random variables that we randomly select. And remember, we know the cumulative distribution of the exponential function is as follows. Because it's a 1-to-1 function that starts at 0 and ends at 1, it's a cumulative function, remember? Because it's a one-to-one function, you can calculate its inverse by just solving for x, so putting x on the side of the equation and everything else on the other side. So we know that this x is uniformly distributed. So for a random number 0.09 and a mu of 3, the simulated waiting time will be 0.0314. So simulating from a distribution, we already know what the mu is. So if you plug this random number and the mu that we have into this equation, you'll find the amount of waiting time in that particular point of time. And this mu will obviously change from state to state. So because we said it's equal to minus the value on the diagonal, 1 over that, whenever you're simulating the amount of waiting time from the 6th state, you have to take the mu from the 6th state. So these two simulations would have had the same mu, but being in the healthy state would have used a different mu. So that's how we simulate from a continuous time random variable. First, a sequence of movements, and then the amount of time we spent in each of those states. The hospital queue example for 3.7 really covers a whole lot of the types of questions that you can normally get for continuous time Markov chains. For each question, I propose that you read it, try to answer it yourself before checking the answer that I will explain. So patients arrive at an A&E department, we call that state A, to wait for an average of 1 hour before being classified by a junior doctor as requiring inpatient treatment, outpatient treatment, or further investigation. Only 1 new arrival in 10 is classified as inpatient, 5 in 10 is calculated as outpatient. If needed, further investigation takes an average of 3 hours, after which 50% are classified as discharged, 25% go to outpatient, and 25% go to inpatient. Outpatient treatment takes an average of 2 hours to complete. Inpatient treatment takes an average of 60 hours. Both results in discharge. It is suggested that a time homogeneous Markov process with states A, F, I, and O, and D could be used to model the progress of patients through the hospital system, with the ultimate aim of reducing the average waiting time in the hospital. So this time you can see, if we had to draw the transition diagram, we're not getting any information about the transition rates directly. In all cases, we are getting the average waiting time. So we are getting 1 over the sum of all the transitions that leave a particular state. And that's typically how information for continuous time Markov chains are presented. So the first question is just to draw the transition diagram. As I said, this is a good time to pause and to try it yourself. But here we have the final diagram. You can see we have the 5 states. And here on the side, you can see some of my calculations. We know, say, starting for 1, from state A, that 1 over small I, F, and O is equal to 1, because we said the waiting time in A is an average of 1 hour. We also know the proportion of people who are classified as I and the percentage that are classified as O. So that's 3 equations, 3 unknowns, and you can solve these rates. And the same goes for all the others. So you can see everything is a one-way street, moving all the way from A to D. Once you've left a state, it's not possible to go back. Okay, keep this picture in mind for the next question. Calculate the proportion of patients who will eventually receive inpatient treatment. Okay. There are 2 ways in which to get to I. Either you leave state A directly, or you're first classified into state F and then you go to state I. There are 2 paths to I. And we know in probability theory, alternative events are summed and events that happen together, or an AND event, are multiplied. So that's the probability of leaving state I directly, leaving to state I from state A, or to first go to F and then from F to I. So the probability of leaving for I is the transition of going from A to I divided by the sum of all the transitions out of A. So it's 1 over 10 divided by the probability on all three of those arrows. Or you could leave to state F, which is 4 over 10 over 1. Just to do that explicitly, it's 4 over 10 divided by the sum of all the arrows leaving A. Times by, so after you've left for I, it is the probability of leaving to I from F. So that is more specifically that number divided by the sum of all the arrows leaving F. To get us to 1/5. Derive expressions for the probability that a patient arriving at time t equals 0 is firstly yet to be classified by a junior doctor at time t, or undergoing further investigation. So it's quite clear that they're asking for conditional probabilities. In this first one, they're asking for the probability of still being in A at time t. And the second question is asking for the probability of being in the state for further investigation at time t. We know everyone starts off in A, and that's the two probabilities we care about. We've proved that the holding time of a state is exponentially distributed. So without even doing the Kolmogorov forward or backward differential equations, we can just always say holding time is exponentially distributed. We also know that once you leave a state, you can't come back, and that's the only reason we can use it. And that's because we know that the probability of being in A all along is the same as being in state A, having had the possibility to leave A and come back, because it's not possible to come back. So we know that this is exponentially distributed, and you could just make that claim and state it directly. So you can see, because from state A, lambda is equal to 1, it's just e to the minus t. But you can verify this using Kolmogorov's equations, and it might be a good exercise to do that. But in the next question, you have to do it anyway. So we're interested in the probability of going from A to F. We know that the derivative of that function can be plugged into the forward differential equation. I'm always picking that one as my standard, but you could be doing the backwards one as well. So all the places where I've put the dots, you can see that we fixed A and F. And now we run through all the probabilities in the middle, A, O, I, F. And technically we're leaving out D as well. Going from A to D. But going from D to F, you can see that that transition rate will be 0. So is going from I to F, because the only way to get to F is directly from A. So we know that this transition is 0, we know that this transition is 0. So it all simplifies to these two statements. We already know the distribution of AAA from the previous question, so we can plug that in directly. Write the differential equation in that form, which allows us to calculate the integrating factor, which is one of the two ways we know how to solve differential equations, either using the log on the one side or just the integrating factor. And going through all the steps, integrating between 0 and t, we get to a final answer at the bottom here. That's the probability of ending up in the further investigation state from the A state at time t. Calculate the expectation of the total time until discharge for a newly arrived patient. This is one of the formulas we've been given. It's not been proven, but we said it was quite an intuitive formula. So going from A to D, let me just explain, popping into the formula, this was 1 over lambda I, which we knew was, or minus lambda I, which we know is 1. And now we fix A and D in this expression again. And if you remember from the expression, we run through the state space, but we leave out the two states that we're interested in. So that's why you'll see I is there, O is there, F is there, but neither A nor D is there. That's just the formula. We run through all the possibilities in the state space except the two states that we're busy with. That's one way to interpret the formula. If you then get to these two states, the expected waiting time of going from I to discharge and O to discharge, normally you would have to plug those into or write out their expected equations using this definition. But we know something extra. We know that leaving from I to D and O to D, there's only one way to go. So we know the expected time of going from I to D is just the holding time. It's 60 minutes or 60 hours. In the case of O, it's 2 hours. So that gives us a bit of a shortcut. So that we know that going from I to D is 60, going from O to D is 2, and we're just left with F to D, which we know there are two ways to get discharged from F. You can either get discharged directly from F, or you can get discharged by going to either I or O. And there's no shortcut for that one. So that's why you'll see on the right here, we repeat this expected value formula for FD. Once we find that we have two equations, two unknowns, and we can solve for the expected time of going from A to D. So if you arrive at the hospital without any further information, on average, people wait 15.5 hours. And that's obviously, some people are saying very few hours, and it's completely offset by people who end up staying in the hospital for many weeks. There's probably a massive variance around that expected value. But, you know, intuitively, as you can see here, most people who come into the A&E, by far the majority of people were not that serious. They just go to outpatient care. It's only 1 in 10 patients, and this is quite typical apparently of a hospital, that there are very, very few very serious cases that come to A&E. Most people are coming for the wrong reasons or overreacting to what's happening to them. Number 5, state the distribution of the time spent in each state visited according to this model. Well, the fact that it's a Markov model, we have proven that the holding time, the time spent in each state, is exponentially distributed with 1 over lambda as the parameter. Describe briefly what additional features of the data might be used to check that this simple model matches the situation being modeled. So we only make 2 assumptions: time homogeneity and the Markov assumption. How do we check either of those? Well, we saw in section 1 that it's possible to test the Markov property using the test on triples. And we can do that test by just looking at the sequence at which someone is moving between states in the continuous time. How do we check time homogeneity? Well, we know that the waiting time in every state is always exponentially distributed if the Markov property holds. So we could do a goodness of fit test on the waiting times and to compare that to the exponential distribution. So it's a bit of an indirect way of testing the Markov assumption. I mean, the time homogeneous assumption. The hospital management committee believes that replacing the junior doctors with a more senior doctor will save resources by reducing the proportion of cases that are sent to further investigation. Alternatively, the same resources could be channeled towards reducing outpatient treatment time. Outline briefly the calculations that would be needed to be performed to compare the options. Well, we are interested in the expected waiting time. So the question stated that we're interested in the expected waiting time of moving from A to D. And we are comparing these 2 values under 2 new sets of assumptions. The first one will say, how do we reduce each of these transition rates under the new budget? So currently we're assuming the way that the transition rates are going is before we are spending the money or these resources channeling new senior doctors instead of junior doctors to certain points in the process. And because we're only interested in testing how long patients wait, we can not say quality of care, which is very difficult to measure. We can update our assumptions in each of these two scenarios where we put senior doctors at different points in the process and compare the impact on the expected waiting time. And that, doing our calculations, we'll nicely be able to compare the trade-offs between classifying people faster versus treating people that are already classified. Discuss whether the current model is suitable as a basis for making decisions of this nature. So I guess the question is indirectly asking for any deal breakers or any problems with the model that would mean that we can't trust the results without caveats, for example. Well, there are 2 points. The Markov property may or may not hold. The time to D from O, in other words, getting discharged from outpatient care, may depend heavily on whether it is coming from A or from F. So patients who are sent for further investigation might be the most complex cases, and those might be cases that take longer to discharge. We don't know. Without testing the Markov property, we wouldn't know. But it's maybe up to the actuary or the modeler to work in conjunction with an expert in the field to be able to decide whether the path by which you arrive at discharge matters. And that's how we'll know if the Markov property is good or not in the first instance. Obviously, if we collect enough data over time, we can test the Markov property. The second issue is probably more important. While the model works for an individual, it doesn't capture the queue length. This cannot be ignored by a good model. So at the moment, we model an individual starting off in the A state, but it doesn't depend, the whole model doesn't depend on how long the queue is ahead of them as they walk into the hospital. It just takes the average rate. And there is definitely fluctuations during even the hours of the day in what those queues are. So you could also say the model ignores fluctuation of queue length on waiting times. Luckily, Stats has developed a lot of good theory around queue modeling, and that's probably where this question came from, and probably the maths or the stats you'd want to use in modeling these hospital queues.